Hello, welcome to today's tutorial. Today we are doing the last part of tutorial sheet 8. That's for PHY 1010. So we'll start with question 5, the one that was given as an assignment to you. I looked at the question. Well, a lot of you did the correct thing. I'm happy. So we'll start with question 5 and go to question 6 and the last one, which is question 7. Okay, I believe tutorial sheet 9 is out already, so people should have started solving some questions already. Okay, so question 5 reads, show that the static force between the block A and the surface can hold the system in equilibrium. So we're talking about this whole system. Can this hold the system in equilibrium? We need to show that. Okay, for the weight of the of block A given, the weight of block A given is 90 newtons. Okay, now the coefficient of static friction is 0.30. That's what we've been given. Okay, so to draw this question, to calculate this question, I drew this diagram. Free body diagrams are difficult for me to draw, but yes, this is what I came up with. So we're going to take the top as positive and the right as positive, okay, meaning the opposites will be negative. Okay, so if we take this as our reference point, all right, if we take the forces with reference to this note, we are going to have forces in the y-axis and in the x-axis. So the forces in the x-axis in this particular case with reference to here, we are going to have 2, okay, which will be T1, that's in the x-axis, T1 will be negative, T1 will be negative plus the other component that will be there is the cosine of T2. So we'll have T2 cos 45. Okay, these two will give us a 0. Then in the y-axis, we are going to have two forces, the weight of the block and the y component of T2. So we'll have T2 sine 45 minus 15, okay, is going to give us a 0. Okay, that's what we have. So we want to find out the value of T1. Okay, can we find T1? Yes, of course we can. We can find T1. Let this be equation 1, this be equation 2. So to find T1, we can use equation 2. Okay, this will be T2 sine 45 being equal to 15. So divide by sine 45, divide by sine 45. T2 is going to be equal to 21.2 newtons. Okay, that's what we have. But, right, hold on. Okay, we have T1 is, sorry, T2 is equals to 21.2 newtons. But the question has asked us to find T1, and from equation 1 we have got T1. Okay, and we know that T1 is equal to T2 cos 45. All right, so T1 is equal to 21.2 cos 45, meaning that T1 is going to be equal to 15 newtons. Okay, that's our T1, the force that is here. T1 is going to be equal to 15 newtons. Okay, so now that we've got the 15 newtons, we now want to find out if the weight, or we now have to show that the the weight of this block can keep the system in equilibrium. Okay, so just here, okay, since we're done with this part, we can focus on this part now. We've got two forces acting on this block with reference to the x-axis. We've got T1, which is in the positive direction, and the force of friction, which is in the opposite direction. Of course, the in the y-axis, we've got the normal and the weight. These are in equilibrium, obviously. So we need to find out the force of friction. Okay, now what is the force of friction? We've been doing a lot of calculations on that. We know by now that the force of friction is equal to, force of friction is equal to the coefficient of static friction multiplied by the normal force. Okay, the normal force, I'm just from saying that it is equal to the weight of the block, so that will be 90. We've been given the coefficient of static friction as 0.3 multiplied by the normal, which is 90. That gives us 27 newtons. Okay, that's the force of friction. Now, if you look at this, the force of friction is 27 newtons. The tension here is 15 newtons, meaning that is not in equilibrium, right? Okay, so the explanation that's there is that this force of friction needs a minimum of 15 newtons for the system to be in equilibrium. So the 15 newtons that we calculated here was the tension in the rope, okay? And if a minimum of 15 newton of friction is needed for us to be able to keep this system in equilibrium. That's the minimum, right? But we have got 27 newtons with reference to the weight of this block. So the 27 newtons is the friction, while the minimum required force is actually 15 newtons. So hence the static friction that can be used to hold this block in position in this particular system is the 15 newtons, but then we've gotten more than that, right? So meaning the system is in equilibrium. The friction force is holding this block from sliding, okay, to keep it in equilibrium. That's what we have for question 5. We now go to question 6. So question 6 reads, a uniform 400 Newton boom is supported as shown. So that's the support that's there. This is the beam and it's hinged, and that's the supporting. So find the tension in the rope. We've got this rope. We're going to have to find the tension and the forces exerted on the bottom, exerted on the boom by the pin at P. So there's this pin at P and we've got the forces, which is this force and this force. That's what we are going to calculate. Okay, so I have this drawing of the same boom. So this is the boom, and the center of mass is exerting a force which I've put as mg, and that is 400 newtons. Okay, then there's a mass hanging from the top there. We've got the hinges coming from here, like, okay. So if this system is in equilibrium, we're going to have the net force. Okay, the net forces in the x have to sum up to 0. The net forces in the y have to sum up to 0. The net torque will have to sum up to 0. Okay, that's what we have. So for the forces, if you look at it, the forces in the x-axis, we've got two forces in the x-axis. We've got the force with reference to P, which is coming from the support, and then there's the force which is with reference to the rope. So that's the tension. So we've got two forces in the x-axis, these two, this one here and this one here. Then in the y-axis we've got three forces. These two, the 200 Newton, 2000 Newton, the weight of the boom, and the force with reference to the P that's from the hinge that's going in the upward direction. And then we've got the tension as well. We are going to have to find the tensions. Okay, so we'll start with the tensions, just so that we'll not have a lot of unknowns. We'll start with the tensions. So the tensions, we're going to take the tension with reference to this point P here. Okay, so like I said in the previous video, the tension in the clockwise direction is taken as negative, and the tension in the anti-clockwise direction is taken as positive. Okay, so the tensions that we have, we'll have just want to put this at a visible position. Okay, that's what we have. So we are going to start with, since we're taking tensions from, the torque with reference to this point. So the first force is the weight of the boom. Okay, so this will give us the force, which is 400 newtons multiplied by the perpendicular distance. So the perpendicular distance is the distance from here to here. Okay, we have this already. Since this is acting at the center of this boom, meaning we are going to have this as L over 2. And the distance from here to here is going to be the sine of this side. Okay, the cosine, the sine of the angle 40 degrees. So I'm going to have the distance will be equal to, of course this is negative since it's clockwise, so we'll have L over 2 multiplied by sine 40. That's that. Then we'll go to the second one, which is obviously this will be anti-clockwise. The torque with reference to the rope. Okay, so the rope is 3L over 4 distance from the hinge. We do not know the tension in this rope, so we'll just write T. But then the perpendicular distance is going to be the distance from here to here. Okay, so that will be 3 over 4 cos 40. Okay, so we'll have T multiplied by 3L over 4 cos 40. Then the last force is at the edge. Okay, this is 3L over 4, this is L over 4, so all of this is L. Okay, that's the length of this rope, of this boom. Now it has a 200 Newton force hanging from there, and the perpendicular distance is going to be the distance from here to here, and that distance will be L sine 40. Okay, so that will be L sine 40 multiplied by 2000 newtons. Okay, so that's the equation we have. Now if we simplify this, we are going to have that's 0.32 multiplied by 400 L, yes, plus 0.575, okay, 0.575, that's cos 40 multiplied by 3 divided by 4 LT, then minus 128.5 L. That's what we have there. If we take, this is negative, that's positive. If we group those that are in the negative, so that the unknowns will go on the other side. We'll remain with T, which is the tension in the rope, is going to be equal to 128 no, it's not 0.5, it's 1285. Okay, this is not point. 1285 plus 128.6, okay, divided by 0.575. Okay, so now you have to be taking the decimal places, the decimal numbers as well, okay, so that you'll be able to minimize on the errors as you are solving. So the tension I have calculated as 2460 point, if you round off, it's still going to give you 24.60 newtons. That's the tension in the rope. Okay, now the question has also asked us to find the force on the boom by the pin at P. Okay, so we've got this pin at P here, where we've got the forces that are acting, where we are supposed to find the forces at this point. Now, if you take note, we've got two forces. We've got the force in the X and we've got the force in the Y. So let's start by finding the force in the X. The force in the X, we are going to calculate it from the top here, where we know that to find the forces in the X, it will be the tension minus the force at P, which is Px, giving us 0. Okay, meaning that the force at Px is going to be equal to 2460, since that's the tension we found. Okay, Newton. Then the forces in the y-axis will have these two forces acting downwards and the force with reference, the force from the P acting upwards. So we'll have the Py minus the center of the weight of the boom minus the 2000 Newton weight. These two will give us Py equal to that will be 2000 plus 400, which is 2400 newtons. Okay, so these are the forces that are acting at the hinge here. We have in the y-axis we've got 2460, and in the in the x-axis we've got 2460, and we've got the force which is in the y-axis, and that force is 2400, meaning their resultant obviously is a force that's going to act in this direction. Okay, now if this force is acting in this direction, it will have the y component and the x component. Definitely that means, okay, let me put it here. It's like the force is here. Okay, then we have this force which is 2400 newtons, and we have another force which is 2460 newtons. These are the two forces. Okay, so to find the resultant of this force, we are simply going to write R. Okay, the resultant R is going to be equal to, okay, we just find the square root already. So we have 2400 newtons plus 2460. This will be squared. Okay, when you simplify this, you're going to get the resultant force that is acting here, this force. Okay, that's what you get. To find out the angle at which it is acting, you simply have to use trigonometry now. You're going to say, you can use the tangent. Okay, you can use the tangent, where you can find it as, since this is the y and x, we know that the resultant tan theta is equal to y over x. So you're going to get the y, which is the y is 2400 divided by 2460, and then you're going to have to solve for theta. So that means you have theta being equal to tan inverse of 2400 divided by 2460, and the value you're going to find is the angle at which this force is acting. Okay, the force the forces exerted on the boom by the pin at P. That's what you have there. Okay, so that's question 2. Sorry, that's question 6. We're now remaining with question 7. Okay. Question 7 is here. Okay, here. So the mast of a sailboat is held by two steel cables attached as shown. So we've got two steel cables. We've got T1 and T2. The front here has a tension of 5,000 newtons. What is the tension in the rear cable? So wants to find out this tension. Okay. Now, what force does the foot? Okay. What force does the foot exert on the sailboat? Neglect the weight of the mast. The foot of the mast is hinged. Okay. Hence, it exerts no torque. So there's a hinge here. It's hinged, and we have that. So we've got two tensions. Okay, the front and the rear. We've been given the tension in the front cable, which is T2, and that is 5,000 newtons. Okay. Okay, so this is the board that I managed to draw. So the tension, this is T1 and this is T2. T2 has been given to us as 5,000 newtons. Okay, 5,000. It's been given to us as 5,000 newtons. We want to find out what T1 is. Okay, now to find out T1, we are going to have to use torque. Okay, we're going to use the condition that the net torque is equal to 0. And if we take torques about this point, okay, if we take this as our reference point and we use it to find our torque, we will have two forces acting. This one acting in this direction and the other one acting in this direction. So now if we take the torque about this point, we'll have these forces which are acting at angles. So we are going to have to take the perpendicular force. Okay, this one will be T2 sine 30. This other one will be T1 sine 45. Okay, because we need the perpendicular forces. So we already have the distance here. We need to simply have this. Okay, so taking like I said, we're taking the talk about this point. So we'll have the perpendicular distance is of course 10 meters multiplied by the first force is T1 is this T1 sine 45. This is anti-clockwise, minus the clockwise one will also be 10 meters times T2 sine 30. Okay, so we can say that these two, if this one goes on the other side, it will be, this is going to be equal to 0. So this will be 0. So if we take this on the other side, it will become positive. Then we'll have 10 meters times T1 sine 45 equals to 10 meters times T2 sine 30. Okay, that's what we have. So if we simplify, we know that T2 is equal to 5,000 newtons. We've already been given that. If we simplify, we're going to get all of what we have this side will give us 25,000. Okay, and this side will remain with T1 equals, so 10 multiplied by sine 45 has given me 7.072. Okay, so meaning that T1 is equal to 36 newtons. Okay, that's what I have as T1. Okay, now the other part asks us to find the force that the foot exerts on the sailboat. Okay, so what force is being exerted by the foot, which is like this foot here, is exerting a force on the sailboat, or can be like that. So to find out that, we're simply going to go for the component of forces in the y-axis. Why are we using the component of forces in the y-axis? Because the force that's coming from the foot is in the y-axis. So the forces that are balancing up with this force are the forces that are coming from these two tensions. Okay, so meaning we're talking about it's not the y-axis actually, it's the x. This is the x-axis, but because I was taking the angle with reference to this point, it was looking like it's the x-axis. But now I want the forces that are in this direction, which is the y-axis. Yes. Okay. So to get those forces, I simply have to take the forces in the x-axis, the forces in the y-axis. I keep mistaking that for the x-axis again. So summation of forces in the y will give us 0, where if we simplify it, we'll have T1, which is this T1, and the component which we're talking about is this, the y component, okay, which is going to be T1 cos 45. So T1 cos 45 plus, okay, the other force is going to be T2 cos 30. That should give us the force from the foot. Okay, if we simplify that, we are getting we're getting 3536, which is the force we calculated here, cos 45 plus T2, which was given as 5,000, cos 30, giving us the resultant that we have. So this will give us 2,500 plus 4,330. This will result in 6,830 newtons. Okay, so the force from the foot is going to be 6,830 newtons. That's what we have. So that's tutorial sheet 8. This is the last question in tutorial sheet 8. Tutorial sheet 9 is already out. You can start attempting the questions, and then I'll go through them as well. In case you've made some mistakes as you were solving, we can meet halfway. Okay, so that's all for now. See you in the next tutorial.